Mitochondrial function is an area of important active research. Furthermore, it has recently been realized that potential drugs should be screened for mitochondrial toxicity, as previous drugs had to be removed from the marketplace due to their side effects involving alterations to normal mitochondrial function. Biolog's OmniLog and PMM platforms provide an effective new approach to assaying mitochondrial activity and mitochondrial toxicology. To gain full value of this slideshow, first-time viewers are encouraged to first watch the Technology Overview slideshow found at the beginning of this slide series. As noted throughout the slideshows in this series, Biolog's platforms are versatile in serving multiple application areas. While this video emphasizes applications in mitochondrial activity and toxicology, Biolog's platforms are also being applied to the characterization, differentiation, aging, and stability of cells and cell lines, cell line and bioprocess development, in cancer research, in studying metabolism and metabolic disorders, and in genotype-phenotype studies. Most cellular functions are driven by energy metabolism, and most of a cell's energy is produced in mitochondrial pathways. Energy metabolism participates both directly and indirectly in chemical toxicology because it drives key pathways such as those involved in the reductive metabolism of xenobiotics, cytochrome P450 metabolism, energy-driven efflux pumps, pathways involved in free radical scavenging, glutathione conjugation, and pathways involved in glucuronide and sulfate conjugation. The Biolog PM assays are fundamentally energy metabolism assays, and they are ideal for monitoring many aspects of mitochondrial function. In microplate wells, a cell is fed different energy substrates. If the cell has a pathway for metabolizing the substrates to produce NADH, this will lead to reduction of a redox dye and formation of purple color in the well. By simultaneously assessing hundreds of these energy-producing pathways, the Biolog technology provides a broad and comprehensive overview of mitochondrial function and mitochondrial deficiencies. Because energy is necessary for cell growth and survival, this technology provides a simple and sensitive means for performing cell growth and death assays. It is similar in many ways to the traditional MTT assay, but much better. This slide shows the superiority of the Biolog MA dye to MTT and other dyes both in sensitivity and in low background color. Its detection sensitivity can go down to about 200 viable cells per well. Biolog's redox dyes MA and MB give an accurate reflection of the number of viable cells, as the amount of purple color formed, measured at absorption 590, correlates linearly with cell number. Here is the first of 4 carbon energy substrate plates showing the specific substrates preloaded into each well. To test for growth and death, cells are seeded into multiple plates on day 0 at 2,500 cells per well. Then, the redox dye is added each day to see if the number of active cells has increased, decreased, or remained the same. In the example shown here, the cells respond differently to various substrates. The red graph corresponds to the cell count on day 0, followed by yellow on day 1, green on day 2, and blue on day 3. For assay of sensitivity to diverse cytotoxic compounds, Biolog provides a set of 4 plates containing 92 different anti-cancer agents. Each of the 92 anti-cancer agents is presented at 4 different concentrations. These plates can be used to compare the chemical toxicity of this standard set to different cell lines. For example, this slide shows a chemical sensitivity comparison of a mouse embryonic fibroblast cell line compared with its RAS-activated isogenic line. Using the Biolog.PM test panels, the chemical sensitivity assays detected an increase in resistance to 17 ions and anti-cancer agents in the RAS-activated cells. In a second example, assay of another isogenic pair of cell lines obtained from ATCC confirms that the DX5 subline is doxorubicin and daunorubicin resistant, but have identical sensitivities to methotrexate. And now we get to the most important topic, the use of our technology to detect mitochondrial toxicity. Referring back to the diagram that we used previously, oxidation of most substrates will result in NADH production by the mitochondria. If the cells are exposed to an inhibitor of mitochondrial function, it will partially or completely block NADH formation and result in partial or complete blockage of color formation. However, most labs perform toxicity assays using cancer cells with glucose as the energy substrate, and because cancer cells exhibit the Warburg effect, they generate NADH using pathways that bypass the mitochondria. Mitochondrial inhibitors, therefore, do not block NADH production from glucose. Here we show how cells exposed to titrated concentrations of the mitochondrial uncoupler CCCP have very different sensitivities in Biolog's assays to 8 different energy substrates. As expected, given the Warburg effect, energy production is barely affected when the cells are given glucose, but strongly affected when the cells are given pyruvate or the other substrates shown. From these studies, Biolog has developed the Tox1 assay plate. It contains 8 diverse energy substrates and allows for testing the mitochondrial toxicity of a chemical over a 1,000-fold concentration range, for example from 0.1 to 100 micromolar. Here we show what can be obtained by using the Tox1 plate to assay the mitochondrial uncoupler FCCP with a special liver cell line that Biolog has engineered. Again, we clearly see differential sensitivities of mitochondrial inhibition depending on the energy substrate, with pyruvate and alpha-ketoglutarate giving the most sensitive detection. Using mathematical clustering to evaluate a set of data on mitochondrial inhibitors suggests that this technology can not only detect mitochondrial toxicity, but may also map the mode or site of action against the mitochondria. In summary, Biolog's assay for toxicology offers numerous advantages. It provides a standard, homogeneous microplate technology format for HTS. It is easy, inexpensive, sensitive, and highly reproducible. It is colorimetric, with no interference from quenching artifacts. It can measure toxicity in diverse cell types, with no cell engineering required. It can also measure toxicity in different cell states, including mitochondrial toxicity, and those studies involving synergy and antagonisms. It can also ensure that cells are consistent assay to assay. In short, a very powerful technology platform. Cell metabolism lies at the core of many key application areas. Understanding this dimension of cellular behavior has important research and commercial value. Biolog's metabolic profiling platforms stand alone in having the flexibility and capabilities to quickly and efficiently serve all these important areas. To discuss your specific application interests, or to explore setting up a trial evaluation of Biolog's phenotype microarray technology, or to place an order, please contact the following departments.